Hello, so for this video we're going to be looking at rotating black holes. Now I'm assuming you've seen the video before this one or through kind of background reading, are familiar with the idea of the event horizon and relating the event horizon to the mass of a black hole. In the last video I also talked about density of black holes. We won't really need them here. But in this video we'll be looking at, if a black hole stops spinning, something we didn't consider in the last video, how does this affect how big a black hole is? This will lead us to considering the possibility of naked singularities. So we're going to go to some interesting places in this video, but this will be about, if a black hole spins, how does that affect, how large the black hole is? So I'll go through this part of the video fairly quickly because it's really about building a, intuition for the effect of rotation and the idea of a centrifugal force. If you'd like more detail on this, I would recommend checking out a video on R-star spherical, where I talk about the effect of rotation in more detail. But since this video is about black holes, I want to spend more time focusing on black holes and a little less time talking about rotation in detail. But it's worth giving a summary because having an intuition for the effect of rotation will help us make sense of how the size of a black hole is related to the rate at which a black hole spins. If we're considering stellar mass black holes, so black holes which are formed by the collapsing of the core of very heavy stars once the star has gone supernova, these cores are spinning very quickly, and to conserve angular momentum as the core collapses, it spins faster and faster, meaning that the black hole that ends up forming, which has quite small radius, at least for stellar mass black holes, spins very quickly. So stellar mass black holes do spin very quickly, and therefore we have to consider spin in a lot of cases. And even black holes at the hearts of galaxies, so really, really massive black holes, they spin also. Now, if you've been on something like a Ferris wheel, you'll know that when it starts spinning, you feel a force kind of like pulling you away from the axis of rotation. You feel kind of like you're being flung out. And this kind of force you feel is a pseudo force, and we call it the centrifugal force. The centrifugal force, you feel like it's pushing you away. Now, the effect this would have if you're in a black hole, say on the surface of a black hole, and that black hole suddenly started spinning, is, you would feel a centrifugal force which in some way would counteract gravity to a degree at least, and so you would feel more weightless. You feel like you have less weight if you were, on the surface of this black hole if it suddenly started spinning. And so, spinning black hole, if you're, co-moving with it, this spin is going to generate a force that's going to a degree counteract gravity, meaning that you can actually get closer to the heart of a black hole with, still having some chance of being able to escape away. Meaning the actual event horizon of a spinning black hole is less than the event horizon of a black hole with the same mass that isn't spinning. But we'll kind of show that mathematically in a bit. But to do that, it's actually easier, instead of considering the rotating black hole generating a centrifugal force, to consider a rotating black hole giving you some kind of angular velocity. So if you're on the surface of the black hole and co-moving with that surface, then as the black hole rotates, you're kind of like rotating with it, and so you have some angular velocity, you have some motion that isn't getting you closer or further away from the heart of the black hole, but it's causing you to kind of move around it. And this extra rotational energy means that you have more energy, on the surface of the black hole, and that has to be taken into account if we're considering how much additional radial kinetic energy you will need to escape the black hole. And that relates to the size of the event horizon of the black hole. But now we've talked a little bit about the idea that kind of a rotating black hole generates a centrifugal force, or kind of equivalently gives you rotational kinetic energy. Let's have a look at finding the total kinetic energy you would have if you're on the surface of a black hole, and then we can use that idea to then find the size of a black hole, because we define the size of a black hole in terms of escape velocity, which will relate to how much kinetic energy you have on the black hole surface. So now we're going to look at finding the total kinetic energy of somebody on a rotating object, and we assume they're co-moving with that rotating object. So in other words, where they are situated on the object is the same, so they kind of like rotate with the same time period as the rotating object, so they are stationary relative to the surface of that rotating object. Well, then the angular frequency of that person is going to be 2 pi divided by the time period for that object to rotate. And sometimes we call this angular frequency, and other times we call this angular velocity. Because clearly if an object is rotating faster, so if the frequency is higher, then the angular frequency is going to be larger. So, since angular frequency tells us about velocity, we sometimes call angular frequency angular velocity. And if somebody is on the rotating object and co-moving with it, then the kind of like velocity associated with that rotation is just going to be the circumference of kind of one complete revolution of the object divided by the time to complete one full revolution. In other words, it's the angular frequency times the radius of that object. Now, I'm using capital V here to refer to kind of, rotational velocity, whereas I'll use lowercase v to refer to radial velocity. So, it's one of those times in physics where, unfortunately, since we're talking about two different kinds of velocities, radial and rotational, we need to in some cases use capital V and in some cases use lowercase v, although that's just my notation. And so the kinetic energy of somebody on the rotating surface of an object just from the object's rotation is equal to half m capital V squared, which is half m omega squared r squared if we plug in our equation for capital V. Now the total energy somebody would have on the surface of a rotating object would therefore equal any rotational kinetic energy they have due to the object rotating plus any radial kinetic energy they have at the instant where they're on the surface, which is trying to bring them away from the object or closer to the object. And if we use lowercase v to refer to radial velocity, we can then factor out the mass of the person on the rotating object, so factor out small m, and we get that the total kinetic energy is half m lots of the radial velocity squared plus omega squared r squared. Now here, it's worth saying, because we're dealing with energy that is a scalar, I'm not really worried about the direction the person is trying to move radially compared to the direction of rotation. of a black hole or an object on the moment they're trying to move away or into the black hole. And that does mean that the the fact that the radial velocity and rotational velocity may be in different directions is a complication I'm ignoring, because well, it just makes this video a little simpler, but it's worth saying for those of you who would like a more rigorous discussion, it's worth keeping that simplification in mind before we go any further. But we've got the total kinetic energy now of somebody on a rotating object, and if we set that equal to the change in gravitational potential somebody would need to move, need to have to get to an infinite distance from the object, then we can work out the escape velocity from that object, and setting the escape velocity to equal the speed of light will give us the radius, capital R, of the event horizon of a black hole. And so now we're going to have a look at calculating the size of a spinning black hole. And by size I mean the radius of the event horizon. Now the event horizon is a region around the centre of a black hole where, on this region, on the surface of this event horizon, the escape velocity is the speed of light. So, in other words, your radial velocity you would need to escape this surface and travel to infinity from the black hole, this radial velocity would equal the speed of light. And so, to find the radius of the black hole, we then set the gravitational potential energy. You again, if you went from the surface of a black hole, or the surface of the event horizon, to infinity, so that's GMM over capital R, where R is the radius of this event horizon, and you set that equal to the total kinetic energy somebody has at their disposal to transfer to this gravitational potential energy and thus escape the surface of the black hole. But for a black hole, when we're looking at kind of the event horizon, we define the event horizon to be a point, a region in space where the escape velocity is the speed of light, and the escape velocity refers to the radial velocity somebody would need to escape the black hole. So, whereas on the last slide we had small v for our radial velocity, here on this slide we have c for our radial velocity, because when v is c, we have an equation that will allow us to calculate the size of this event horizon. And if we were to arrange it, we get this cubic polynomial in R. Now, if you want to solve cubic polynomials exactly, the method I'm familiar with, developed by an Italian mathematician, and it's a really cool method, but it involves the use of complex numbers, and many people are not comfortable with complex numbers. So if you want to solve it kind of numerically, a good thing to use is the Newton-Raphson method. That provides really good approximate solutions in this particular case. But when you solve this polynomial equation, you get this relationship between the radius of the black hole and the angular frequency of the black hole. So we can clearly see that as a black hole spins faster and faster, its radius, diminishes. That is, the size of its event horizon drops. Now, if you do this kind of argument within the context of general relativity, it actually turns out, if you look at the metric describing the space-time around a black hole, if a black hole spins fast enough, the event horizon drops below the radius swept out by the matter at the heart of a black hole, meaning that the matter at the heart of a black hole, which at least classically, by which I mean non-quantum mechanically, has infinite density, is then exposed and not protected by an event horizon. And we call this kind of exposed infinitely dense matter, we call it a naked singularity. It's very troubling if such things exist, because our laws of physics can't currently really handle, as far as we understand them, infinitely dense materials, but there are some research that have been done on the possibility, just in case, when astronomers look into the sky, we happen to find evidence for clear singularities, where that singularity has become a naked singularity. There are some suggestions that say that these singularities should emit light, but it's very unclear really exactly what would happen. In fact, many physicists don't really believe that a singularity is actually a physically realised solution to Einstein's field equations describing a black hole. So, but what all physicists do agree on, at least to my awareness, is that if a black hole spins faster, its event horizon actually drops. Which means, if we define the size of a black hole according to its event horizon, fast spinning black holes are actually smaller than they would be if they were not spinning very quickly. And if you insist that there are no naked singularities on the universe, then since there being no singularity places a limit on how small an event horizon can get, at least compared to the radius of the matter at the heart of a black hole, well, the radius it sweeps out when it moves in a circle, then actually insisting that naked singularities don't exist places a kind of limitation on how quickly black holes can spin. So there's also research into spinning black holes where people are wondering, is there actually any physical laws which would ensure that black holes can't spin fast enough to allow for the existence of naked, can't spin fast enough to form naked singularities at the heart. Now, if we want to see, how the event horizon changes as we add mass into a black hole, you can also, create a plot based on the equation we had before, and we have this where, each curve represents a black hole rotating at a different angle of frequency. And when looking at this curve, looking at these curves, we can see an interesting trend. As we increase the angle of frequency, we flatten out the response of how much the radius of a black hole increases if we increase its mass. So for very fast spinning black holes, if you give them additional mass, the radius will increase much less than you would expect if the black hole wasn't spinning. Now, it's worth saying throughout this video I've made a few approximations. Firstly, when calculating the velocity, radial velocity you have on the surface of a black hole, I've assumed firstly that the radial velocity is constant because I'm assuming that the black hole is spherical. However, if a black hole is rotating very quickly, then the black hole wouldn't be spherical. Additionally, I'm taking the rotational velocity of someone on a black hole to be the rotational velocity at the equator of a spherical black hole. However, if you're on the pole of a spherical black hole, you're not going to gain any kinetic energy from the rotation of the black hole because the pole isn't rotating because it's along the axis of rotation of the black hole. So there's a lot of approximations going in here, but physics is all about modelling. It's about working out what approximations you can use, and also what approximations in other cases is ideal really not to use. But for what is intended to be a short video, I didn't want to go. Didn't want to, have a very complicated equation, because also I appreciate very complex and long equations are not the most friendly or approachable, particularly for YouTube content. So coming up on this channel, I'm hoping to do at some point a video about spinors. Doing some reading on that. I'm also doing some reading on decoherence to create a follow-up video to the video I made about decoherence, so looking at decoherence in more detail. And part of my motivation to look at spinors is to develop my understanding of Dirac's equation, such that I can make a really good video about the quantum mechanical properties of tachyons. Well, going back to my relativity playlist. So that's what's coming up on this channel. But yeah, it worth saying, at the moment I'm also writing a story, and so with the story and with work and stuff, I will still be making a playlist on either stellar physics, general relativity, or string theory. But I'll be deciding which ones to do by looking at the votes on the poll by the end of this month. So if you would like a playlist on either stellar physics, string theory, or general relativity, check out that poll, and whichever option has the most votes, that's what I'll be doing. But anyway, I hope you got something out of this video, learnt a little bit about rotating black holes, and also naked singularities, and hopefully see you for another video fairly soon.